Hello friends, today we will be discussing the part 2 of fluid flow in food processing. This second part on fluid flow in food processing will help you to understand following aspects: the continuity equation, Reynolds number, flow measurement using pitot tube, orifice meter, venturi meter, and finally we will end with conclusions. First section, the continuity equation. When a fluid is in motion, it must move in such a way that mass is conserved. The principle of conservation of matter is frequently used to solve problems related to fluid flow. To understand this important principle, consider a fluid flowing in a pipeline as shown in the figure 1. Since the fluid is moving, suppose that in time step delta t, the fluid occupying the space x bar moves to space y bar. The distance between x and y is delta x1, and between x bar and y bar it is delta x2. The cross sectional area at x is dA1 and x bar it is dA2. We have selected different cross sectional areas at the two ends to show that our derivation will be applicable to such variations. For the matter to be conserved, the mass contained in space x bar must be equal to that of y bar. The fluid contained in the space yx bar is common to both initial and final space. Therefore, the mass of fluid in space xy must be equal to that of x bar y bar. Thus, rho 1 A1 delta x1 is equal to rho 2 A2 delta x2. So, divide this equation 28 by time step delta t and you arrive at rho 1 A1 delta x1 by delta t is equal to rho 2 A2 delta x2 by delta t. If you put limit delta t tends to 0 on either side of equation 29, you arrive at rho 1 A1 u1 bar is equal to rho 2 A2 u2 bar, where u bar is the average velocity. So, in case of u1 bar it will be equal to dx1 by dt, in case of u2 bar it will be equal to dx2 by dt. This equation 30 is known as equation of continuity. We can express this equation on the basis of either mass flow or volumetric flow rate. Therefore, rho A u bar is equal to m dot. This equation 31, m bar stands for mass flow rate, that is kilogram per second. The mass flow rate is a function of density rho, the cross sectional area A of the pipe or tube, and the mean velocity u bar of the fluid. Equation 31 shows that mass flow rate remains constant under steady state conditions. For an incompressible fluids such as liquids, the density remains constant. Therefore, the equation 30 can be rewritten as A1 into u1 bar is equal to A2 into u2 bar. Otherwise, A into u bar is equal to v dot. The volumetric flow rate v dot is a product of cross sectional area A of the pipe and the mean fluid velocity u bar. According to equation 33, under steady state conditions, the volumetric flow rate remains constant. The preceding mathematical development will be valid only if you use mean velocity u bar for the given cross section. The use of the bar on the symbol u indicates that it represents a mean value for the velocity. Section 2, Reynolds number. Let us do a simple experiment by carefully injecting a dye into the liquid flowing in a pipe. At low flow rates, the dye moves in a straight line manner in the axial direction as shown in the figure 2. As the flow rate increases, the dye begins to blur at some distance away from the injection point. The blurring of the dye is caused by movement of the dye in radial direction. At high flow rates, the dye becomes blurred immediately upon injection. At these high flow rates, the dye spreads in a random manner along both the radial and the axial direction. The straight line flow observed at low flow rates is called laminar flow. At intermediate flow rates, the flow is called transitional flow. And finally, the erratic flow obtained at higher flow rates is called turbulent flow. The flow characteristics for laminar flow are influenced by liquid properties, flow rate, and the dimensions of the liquid-solid interfaces. Based on the experiments conducted by the scientist called Reynolds, the inertial forces are a function of liquid density, that is rho, tube diameter d, and the average velocity u bar. The viscous forces, on the other hand, are a function of liquid viscosity. A dimensionless number named after the scientist, called as a Reynolds number, is defined as the ratio of the inertial to the viscous forces. It is depicted mathematically in equation 34. NRE, that is the Reynolds number, is equal to inertial forces divided by viscous forces. In terms of physical quantities, NRE is equal to rho into u bar into d divided by mu. If instead of average velocity u bar, the mass flow rate m dot is measured or given, then substituting equation 31 in equation 35 and rearranging the terms, we obtain NRE is equal to 4 into m dot divided by mu into pi into d. A Reynolds number is most useful in quantitatively describing the flow characteristics of a fluid flowing either in a pipe or on the surfaces of the objects of different shapes. As long as the Reynolds number is 2100 or less, the flow characteristics are laminar or streamline. A Reynolds number between 2100 and 4000 signifies a transitional flow. A Reynolds number greater than 4000 indicates turbulent flow, denoting small influence of viscous forces on energy dissipation. Bernoulli equation. Bernoulli's equation given below governs the flow measurement of fluids in food processing. Its derivation and equations involved, that is equation 37 to equation 46, are depicted in FAQs of this module. Flow measurement. The measurement of flow rate in a liquid transport system is an essential component of the operation. Flow measurement is the quantification of bulk fluid movement and is commonly measured during food processing steps for the fluids involved in unit operations. Moreover, only by measuring we can control the flow. Therefore, periodic measurements during the actual operations are required to ensure that the system components are performing in an expected manner. There are several types of flow measurement devices that are inexpensive and lead to direct quantification of the mass flow rate or velocity. These include pitot tube, orifice meter, and venturi meter. With all three of these methods, a portion of the measurement involves pressure difference. The device most often used for this purpose, that is to measure the pressure difference, is called U-tube manometer. Let us first consider how a U-tube manometer is used in measuring pressure, then we will examine its use in flow measuring devices. A U-tube manometer is a small diameter tube of constant diameter shaped as U as shown in the figure 3. The tube is partially filled with a fluid called as a manometer fluid, rising to a certain height in each of its arms. This fluid must be different from the fluid whose pressure is to be measured. Mercury is a commonly used as a manometer fluid. Let us consider a case where we want to measure pressure at a location A in a vessel containing some fluid as shown in the figure 4. For this purpose, a hole is drilled in the side of the vessel at the same elevation as location A, and one arm of the U-tube is connected to this hole. As shown in the figure, the pressure of the fluid in the vessel pushes the manometer fluid down in the left hand arm while raising it by an equal distance in the right hand arm. After the initial displacement, the manometer fluid comes to rest. Therefore, we can apply the expressions for the static head. To analyze the pressures at various locations within the U-tube manometer is to account for pressures at selected locations starting from one side of the manometer and continuing to the other. Using this approach, we note that pressure at location 1 is same as at A because they are at the same elevation. From location 1 to location 2, there is an increase in the pressure equivalent to rho 1 g Z1 or rho 1 g Z1. Pressures at locations 2 and 3 are the same because they are at the same elevation and the fluid between locations 2 and 3 is the same. From location 3 to 4, there is a decrease in pressure equal to rho m g Zm. The manometer fluid at location 4 is exposed to atmosphere. Therefore, we may write an expression as follows: Pa plus rho 1 g Z1 plus rho m g Zm is equal to P atmosphere, and this equation is derived basically from the Bernoulli's equation. Pa is equal to rho m g Zm minus rho 1 g Z1 plus P atmosphere. If the density of the manometer fluid rho m is much larger than the fluid in the vessel rho 1, then pressure at location A in the vessel is simply Pa is equal to rho m g Zm plus P atmosphere. Therefore, knowing the difference between the heights of the manometer fluid in the two arms, that is Zm, and the density of the manometer fluid, we can determine the pressure at any desired location in the vessel. Note that the lengths of the manometer arms have no influence on the measured pressure. As shown in the figure, the pressure of the moving fluid measured at location 1 is the static pressure. If the pressure sensor were moving with the fluid at the same velocity as the fluid, then the fluid would appear static to the sensor, hence the name. A common procedure to measure static pressure is to drill a hole in the duct, making sure that there are no imperfections in the hole such as burrs, so that the fluid moving in the duct is not disturbed. A pressure measuring device such as piezometer tube is connected to the hole at location 2 to measure the static pressure as shown in the figure. Using the same approach as for a U-tube manometer to track pressures at various locations, as discussed in the previous section, the pressure at location 1 is P1 is equal to P3 plus rho GZ2 plus rho GZ1. Since P3 is equal to 0 because it is the gauge atmospheric pressure, then P1 is equal to rho G into Z1 plus Z2, which is equal to rho G Z3. If we insert a tube B into the duct as shown in the figure, some of the fluid will be pushed through the tube to a height Z4 in the tube. After a short transient period, the fluid inside the tube will come to rest and its velocity will be 0. This would imply that at the entrance of the tube at location 4, the fluid velocity is 0 and it is stagnant. Therefore, the pressure of the fluid at 4 will be the stagnation pressure. Applying the Bernoulli's equation to the locations 1 and 4, assuming they are at the same elevation, we have P1 by rho plus U1 square by 2g is equal to P4 by rho. Therefore, the stagnation pressure P4 is equal to P1 plus rho U1 square by 2g. This equation, that is equation 47, the term rho U1 square by 2g is called the dynamic pressure because it represents the pressure due to the fluid's kinetic energy. The stagnation pressure P4 is the sum of the static and dynamic pressures, and it is the highest pressure obtainable along a given streamline, assuming that elevation effects are negligible. Coming to the first flow measurement device, that is pitot tube. A pitot tube is a widely used sensor to measure velocity of a fluid. The design principle is based on the existence of stagnation and static pressures when an object is placed in the following fluid. A schematic of a pitot tube is presented in the following figure. The outlets of the pitot tube are connected to a U-tube manometer to measure the differential pressure. The inlet hole at location 1 measures the stagnation pressure. If the pressure and velocity in the fluid at location A upstream of 1 are PA and UA, and elevation difference 1 and 3 is negligible, then P3 is equal to PA plus rho F UA square divided by 2. At location 2, the static pressure is measured. If the elevation difference between locations 2 and 4 is negligible, then P4 is equal to P2 is equal to PA. Then from equation 48 and equation 49, we get P3 minus P4 is equal to rho F UA square divided by 2, or UA is equal to square root of 2 into P3 minus P divided by rho F. We obtained this equation using the Bernoulli equation, which requires the fluid to be inviscid. In other words, the viscosity is equal to 0. This equation may be modified for the real fluids by introducing a tube coefficient C. Therefore, the equation 50 will become UA is equal to C into square root of 2 into P3 minus P divided by rho F. This equation indicates the fluid velocity in a stream at any desired location can be determined using a pitot tube by measurement of the pressure difference. If a U-tube manometer is used with the pitot tube as shown in the figure, then we can follow the same approach as given earlier in this section to account for the pressures at various locations. We can measure the velocity directly from the change in height of a manometer fluid, that is Zm, when the two sides of the U-tube manometer are connected to the two outlets from the pitot tube. Section 3.2, Orifice meter. By introducing a restriction of known dimensions into flow within a pipe or tube, we can use the relationship between pressure across the restriction and velocity through the restriction to measure the fluid flow rate. An orifice meter is a ring introduced into a pipe or tube that reduces the cross-sectional area of the tube by a known amount. By attaching pressure taps or transducers at locations upstream and downstream from the orifice, the pressure changes can be measured. We again use equation 45 to analyze flow characteristics in the region near the orifice. Reference location A should be at sufficient distance upstream that the orifice does not influence flow characteristics. Reference location B is just slightly downstream from the orifice, where velocity is the same as within the orifice. The figure illustrates the flow stream profile around the orifice meter and the reference locations. The pipe diameter is D1 and the orifice diameter is D2. Hence, using equation 45, we get UA bar square divided by 2 plus PA by rho F is equal to UB bar square divided by 2 plus PB by rho F. Here UA bar is equal to A2 by A1 UB bar, which is equal to D2 square by D1 square into UB bar. Therefore, UB bar square divided by 2 plus PB by rho F is equal to D2 by D1 whole to the power 4 into UB bar square divided by 2 plus PA by rho F. This equation allows computation of velocity at location A from the pressure difference PA minus PB and the diameter of the pipe or tube D1 and the orifice diameter D2. Note, C is the orifice coefficient. If we use a U-tube manometer to determine pressure drop, then we can use the same approach as shown earlier in the section and obtain the following equation. Section 3.3, Venturi meter. To reduce energy losses due to friction created by sudden contraction in the flow in an orifice meter, a Venturi tube of the type illustrated in the following figure can be used. An analysis similar to that presented for the orifice meter leads to the following equation. The average velocity at location 2 U2 is given by the following equation. Here, the average velocity is U2 bar is at reference location 2, where diameter D2 is the smallest value for the Venturi. The Venturi meter requires careful construction to ensure proper angles of entrance to and exit from the Venturi. The meter requires a significant length of pipe for installation compared with the orifice meter. In general, the orifice meter is less costly and simpler to design than the Venturi meter. However, there are certain advantages using Venturi meter in the industrial scale. Some of them are as follows. The Venturi tube is suitable for clean, dirty and viscous liquids such as liquid chocolate, honey and some slurry services. Accuracy is 1% of the full range. There is not much wear and tear of the instrument, and it can be used for large flow rates and large diameter pipes. Conclusions. In this module, continuity equation is derived, which forms the basis for understanding fluid flow. Reynolds number, which is a qualitative expression of the ratio of inertial to the viscous forces, provides an insight into energy dissipation caused by the viscous effects on fluid has been covered. If Reynolds number is 2100 or less, the flow characteristics are laminar or streamline. A Reynolds number between 2100 and 4000 signifies a transitional flow. A Reynolds number greater than 4000 indicates turbulent flow, denoting some influences of viscous forces or on the energy dissipation. It is essential to monitor or control the flow of various fluids through pipes, ducts and assorted vessels in food industries. These fluids can range from thick oils to light gases. In this module, some of the standard procedures or instruments such as pitot tube, orifice meter and Venturi meter for measuring the fluid flow has been discussed. Thank you.